ಆದಷ್ಟು 5 minutes 2 minutes 10 minutes ಜಾಸ್ತಿ ಆಗುತ್ತೆ ಯಾಕಂದರೆ.
Hello, welcome back. Today we will discuss about the mesh analysis. Okay, first of all, what is actually a mesh? Before that, we will have to know what is actually a loop. And loop is basically any closed path in the network. Now, for example, if this particular network is considered, so we can have or we can observe 3 closed paths. One is this, and the second one is this, and the third one the outer loop. Okay, so there are basically 3 loops in this particular network. Now, what is actually a mesh? You know, mesh is the most fundamental form of the loop, okay, which cannot be further divided into some more closed paths. Now, what you observe is this, it is also a closed path, no doubt in that, but that cannot be further divided into some more closed paths. Okay, so this is the mesh, this is the mesh. So then this one cannot be a mesh because this particular closed path is again divided into 2 more closed paths. So this particular network has got 3 loops and 2 meshes, right? Now, what we do in the mesh analysis? Mesh analysis is also one of the methods of analyzing the network to obtain the response or solution of the network. What we basically do here is we identify the meshes in the given network, we allocate a current to each of the meshes, then we will apply KVL to each of the meshes. So, if there are 2 meshes available, then there will be 2 equations resulting in due to the application of the KVL, and those 2 equations will be in terms of the mesh currents. Then when we solve those equations, we will get the mesh current values, and take it from me, if you know the mesh current values, you can find the response at any point of network, and sometimes the mesh currents themselves will be the response of the network. So, this is what you have to remember, right? So, now let me illustrate how this mesh analysis is carried out. Now, here our objective is to find the mesh currents. Now, let me reiterate whatever I have told. What we do in mesh analysis? We identify the meshes in the given network, then we allocate a current to each of the meshes, then we apply KVL to each of the meshes. If there are 2 meshes, that will result into 2 equations in terms of the mesh currents. Then when we solve those equations, we will get the mesh current values. Then if you know the mesh current values of any network, you can find the response at any point of network. So, we will do the same thing. First, we will identify the meshes. We have already identified that there are 2 meshes. So, we allocate a current to each of the meshes. So, this is the current allocated, say this is I1, this is I2. And we always consider the mesh current direction to be always in clockwise direction. Now, in actual, if it is in the anti-clockwise direction, it does not matter. When we calculate, we get the value in terms of negatives, that is all. Okay, so that is not at all a problem. Okay, so we will consider the mesh currents to flow in the clockwise directions, right? Now, this particular arm only belongs to mesh 1, so current in this arm can be only I1, and this particular arm belongs to only mesh 2, so the current in this particular arm can be only I2. This particular arm or the branch, okay, belongs to both the meshes, so whatever the current that flows through 4 ohms will be the resultant of I1 and I2. So, this is what you have to remember. So, what we have done, we have identified the meshes, we have allocated a current to each of these meshes, and we will now have to apply KVL to each of these meshes. So, before the application of the KVL, we need to make sure of the polarities of the potential drops that takes place across the elements that we come across in the mesh, right? So, this is what we do, okay, but we do this for the one last time. For the next problem and onwards, when we apply the KVL to the mesh, so we will not identify any polarities. So, we can directly write the equation without identifying the polarities of the potential drop that takes place across the elements. Okay. So, for the one last time we will identify. Now, already I have told that you know, this mesh current is flowing in the clockwise direction, so that makes what? The I1 to flow in this way, and I2 will flow in this way, right. Now, if the current that flows in this direction, okay, is, you know, if it is flowing in this direction, the polarities of the potential drop can be plus minus left to right. Always the entry point, yesterday I have told you, always the entry point will have the positive polarity of the potential drop that takes place across the passive circuit element. Please remember, this is true for the passive circuit element. So, now this goes in this direction, so obviously the potential drop can be what? Plus minus left to right. And now here this one is basically shared element between the two meshes. So, what we will do is, okay, we will consider the resultant current to flow from top to bottom, and when we calculate this current, you know, by applying KCL here, so it is nothing but what? I1 minus I2. So, what I will do now? I1 minus I2 is the current that flows from top to bottom. How did I calculate that? This current is equal to this current plus this current. So, this current is now equal to obviously this minus this. So, I1 minus I2. So, now when the current flows from top to bottom, the polarity of the potential drop can be what? Plus minus, okay, top to bottom. Okay. So, this is now we are very much sure about the polarities of the potential drops that takes place across the elements in each of these meshes. Now, we will apply what? KVL to each of these meshes. So, first apply KVL to mesh 1, right. So, we start from here, you are encountering plus, and you know the drop across the resistance is always given by the current that enters the positive polarity of the potential drop and multiplied by the resistance value itself. So, plus 2 I1, and we come here plus 4 into I1 minus I2, then minus 10 is equal to 0. Then this can be rearranged to what? 6 I1, then minus 4 I2 is equal to 10, call this as equation 1. Next, we have applied the KVL to mesh 1. Now, we will apply KVL to mesh 2. Apply KVL to mesh 2. Apply KVL to mesh 2. So, plus 3 I2, then plus 2, then minus, you get observing minus this drop. Had it been gone this way, you know, you would have got 4 into I1 minus I2. We are going in this direction, you are encountering minus polarity. So, you can write it as what? It is the same drop, but with a negative sign. So, minus 4 into I1 minus I2. Okay. So, 3 I2 plus 2, and then minus 4 into I1 minus I2. So, which is now equal to 0 according to the KVL. Now, this will be rewritten, but in a different way. Observe 3 I2 plus 2, this minus into minus plus. So, plus 4 I2, then minus 4 I1. So, I have written in this way. It is the same term, but written in this way. So, this is equal to 0. Then rearranging this, so we will get this as minus 4 I1 plus 7 I2 is equal to minus 2, call this as equation 2. So, I want you to observe this particular equation and this particular equation, and what is that which you have to observe importantly is the drops across the passive circuit elements. They are always what? By default plus, they are by default plus. Okay. So, 2 I1 plus 4 into I1 minus I2, 3 I2 plus 4 into I2 minus I1. So, in the next problem onwards, you need not worry about the polarities of the potential drop that takes place across the passive circuit element. So, directly it is what? You know, you will write plus and whatever the drop, okay, that is whatever you get by multiplying the resistance value with the corresponding current. But here what you need to remember is, if the element is shared by two meshes, like in this case it is shared by 1 and 2. So, if you want to write the potential drop across the 4 ohms, when you are applying KVL to mesh 1, blindly you write plus 4 into I1 minus I2. Now, if you are applying KVL to mesh 2, and if you want to write the potential drop across the a 4 ohms resistor, you are applying KVL to mesh 2 now. So, plus 4 into I2 minus I1. Okay, if you are applying KVL to mesh 1, it should be written as what? 4 into I1 minus I2. If you are applying KVL to mesh 2, and if you want to write the potential drop across 4 ohms, blindly you can write it as plus 4 into I2 minus I1. Automatically everything will be taken care. So, from now onwards we will not consider any polarities of the potential drops across the passive circuit element. Directly we will be able to write that. Okay, but still we will be writing correctly. Okay, so then these two are the equations. I have told if these two equations will be in terms of the mesh currents, So, when we solve these two equations, we will get the mesh current values. So, equation 1 and 2 in matrix form, okay, so will be written as 6 minus 4, then minus 4, then 7, then multiply 2 I1 I2, then this is equal to the 10, then minus 2. This is the matrix equation which result, okay, from these two equations. And then when we solve this matrix equation, we will get what? I1 and I2. So, how do I get that now? First we will calculate the determinant. So, which is now equal to 6 minus 4 minus 4, 7. So, which is 42 minus 16. So, which is 26. Next we will calculate delta I1, you know the Cramer's rule, we are basically applying the Cramer's rule. So, using Cramer's rule, okay. So, now delta I1, so write this right hand side in the first column to get the delta I1. So, 10 minus 2 minus 4, then 7. So, what is that you get is 70 minus 8, 62, whatever you are going to get. Then delta I2, so which is now equal to, you know, 6 minus 4, then 10 minus 2. So, what you will get is minus 12 plus 40, so which is 28. So, how do I get the mesh current values now? Okay, you know all this. Okay, so I1 is now delta I1 by delta, so which is, you know, 62 divided by 26, 62 divided by 26. So, turns out to be somewhere around 2.384 amperes. Similarly, you can calculate the I2. So, I2 is delta I2 by delta, so which is, you know, 28 by 26. So, which you will get it as 1.076 amperes. So, now this is how you calculate the mesh currents, whether it is the problem of 4 meshes or 3 meshes or 5 meshes, this method remains the same for calculating the mesh currents. Okay. So, I1, I2 now we have found. Now, I have made a point earlier that if you know the mesh currents, you can find the response at any point of network, Now, let us consider that we want what? Vx here, and the current that enters what? The positive polarity, okay, say Ix here. Now, whether this Vx and Ix, can they be determined by using the mesh currents? Of course, yes. How? Let us see. So, from the circuit, what is Vx? Vx is given by what? The current that enters the positive polarity multiplied by the resistance, okay, 3 ohms. So, it is I2 into 3 basically. So, which is what? You can write it as 3 into 1.076. So, which turns out to be 3.228 volts, okay. And if you want Ix, you know, Ix is the current, okay, which is of our interest, and we want to find that current which is actually entering the positive polarity of the 2 volt source. So, what I will do now? So, Ix, you know, this belongs to only this particular mesh. So, we have seen that I2 is the current which flows in this arm in this direction, okay, in this direction. So, what we can say? I2 is in perfect alignment with Ix. So, I can write Ix is in fact what? I2, which is given as 1.076, which is actually 1.076 amperes. And now, supposedly if you want one more current which is flowing in this direction, and we call it as say IY, and what you are observing, I1 we have already considered, and that considered current is flowing in this direction, and we have already found that, which is basically the mesh current. IY, whatever the current we require, it is flowing in this direction. It actually means what? These two currents are in opposite directions, so you can easily write IY as minus I1, and which you can easily get it as minus 2.384 amperes, So this is how we obtain the responses, or rather the mesh currents, and then the responses, okay, by applying the mesh analysis. So what we have done, we have first identified the meshes, we have allocated a current to each of these meshes, then we applied KVL to each of the meshes, and we got the equations in terms of the mesh currents, then we solved those equations, we got the mesh current values, and using those mesh current values you can find the responses at any point of network, and that is what we have done in this particular illustration problem. So this marks the end of the problem. Now we will go to the second problem. I hope you have all followed this. So we will go to the second problem. So what it says, the statement, find the power delivered or absorbed by each source in the network shown. Now it is not guaranteed that whether all these sources deliver the power or absorb the power. So whether it is delivering the power, if it is delivering the power, find the power delivered value. If it is absorbing the power, find the power absorbed value. So that is what is asked in the question. So you find what? There are three sources, 125 volt source, 50 volt source, these are independent sources, and there is a current source, 0.2 VA, okay. The voltage value which appears across the 5 ohms basically governs the value of this current source. So this current source should be rightly referred as voltage controlled current source. The voltage drop here will actually control the value of the current, okay, that flows out of this current source, right. So now you have to use the mesh analysis, okay. So I will continue this problem, use mesh analysis to find the power delivered or absorbed, okay, by each of these sources, okay. Now before proceeding towards the mesh analysis, what you have to know regarding the power delivery or power absorbed, okay. So this is of course a little bit out of the problem, okay. So what I am trying to tell you here is, okay, the power delivered by the voltage source, okay, what situation will be there in the voltage source when it is actually delivering the power, right. So now if this is the voltage source, right, say this is V, okay, and this is R. When it is delivering the power, always, in this case there is only one voltage source, and always current comes out of what? Positive polarity and ends at the negative polarity. This is what we know. Current flows from higher potential point to lower potential point, and this is the energy absorbing element, this is the energy delivering element, since this is the only one. Now what you can say, if there is a voltage source which is delivering the power, always current comes out of the positive polarity. This is what you have to remember. Whenever a voltage source delivers the power, okay, so the current comes out of the positive polarity of the source. This is what you have to remember. And let us say this current to be what? I. And how to find the power delivered value? What you need to do is just P delivered is actually equal to VI. What is this VI? Voltage source value multiplied by the current that comes out of the positive polarity of the source. Now you may ask, can there be the case wherein the power being absorbed by the voltage source? Yes, of course. Consider this situation. Now. Okay, say this is 5 volt source, and this is 3 volts, and this is 2 ohms. So now in this case this is higher in value as compared to this. So, current has to come out in this way, and the current value is what, 5 minus 3 divided by 2, so which is actually 1 ampere. Now, in this case you are observing, with respect to this source, you are observing what, the current to come out of the positive polarity. So, this is what, delivering the power, and now the current is entering the positive polarity. So, this 3 volt source is in fact what, the power, in fact it is absorbing the power. So, how to calculate the power absorbed? Okay, there is nothing big in that. So, what you need to do, 3 multiplied by the current that enters the positive polarity, then that will give you what, power absorbed. Okay, power absorbed. And if you try to calculate the power delivered value here, if you try to calculate the power delivered value, so that means you have to concentrate what, concentrate on the current that comes out of the positive polarity. So, 3 into what is the current that comes out of the positive polarity? It is minus 1. So, you will get the negative value. So, 3 into minus 1, minus 3. You have calculated power delivered value and you have got it as minus 3 watts. That is the indicative of what? In fact, the power is not delivered but absorbed. Okay? So, in this case, this is delivering the power, this is absorbing the power. And if you want to find the power delivered value by the source, what you need to do? Just multiply the voltage source value with the current that comes out of the positive polarity. This is what you have to remember in the case of voltage source. Now, in the case of the current source, now this is the current source. This is the current source, say I and R. It is, now it is very much obvious that there is only one energy source and it has to what? Deliver the power. It has to deliver the power. Then, you know, if the current goes in this direction, the polarity of the potential drop that takes place across the passive circuit element R, okay, so will be at the entry point. Okay, the positive polarity will be at the entry point of the current. So, plus to minus, top to bottom. So, this is what is V. Now, if you consider these 2 points and these 2 points, the potential between these 2 points should be same as these 2 points. So, what you can conclude now? What you can conclude, if there is a current source which is actually delivering the power, the voltage drop across the current source will always have positive polarity coinciding with the arrowhead, will always have the voltage drop coinciding with the arrowhead. This is what you have to remember. And how to find the power delivered value? How to find the power delivered value of the current source? What you just need to do is P delivered is equal to current source value multiplied by that particular voltage across the current source which has got the positive polarity coinciding with the arrowhead. That is all. And there can be the case of what? Even the current source absorbing the power. So, wherein you will observe that the voltage drop will have positive polarity, okay, not coinciding with the arrowhead. That means it will appear here, it will appear here, and the negative polarity will coincide with the arrowhead. So, in that case you can say that the current source is in fact absorbing the power, is in fact absorbing the power. So, let us keep all these things in our mind and let us calculate the power delivered by each of these sources. Okay, right. So, and of course, this we are doing by using what? The mesh analysis, right. So, first thing what we need to do in the mesh analysis is to identify the meshes. So, 1, 2, 3, there are 3 meshes, say I1, I2, we have allocated a current to each of these meshes, I1, I2 as well as I3. Now, what we will do is just the observation. First, what we need to do is, you know, what we want, that we need to remember. So, power delivered, so power delivered value, so power delivered by 125 volt source is now equal to, as already told, 125 the voltage source value multiplied by the current that comes out of the positive polarity. This particular arm only belongs to what? Mesh 1. The current that flows in this arm is actually I1. So, I1 comes out here. This is I1 which comes out. So, 125 I1. Is that clear? Next, P50. So, this is nothing but the power delivered. Okay. So, power delivered by the 50 volt source. Power delivered by the 50 volt source. How do I calculate that? 50 voltage source value multiplied by the current that comes out of the positive polarity. So, here let me tell you, we are just assuming that all these sources are actually delivering the power, okay. But when we calculate, if it turns out to be a positive value, it actually means that it is indeed delivering the power. If it turns out to be a negative value, Okay, it means what? Power delivered value is a negative value, which only indicates that it is absorbing the power. Okay, so first we assume that they are all delivering the power. If we calculate that and if we find that to be negative, so you have to interpret that as power absorbed. Okay, so 50 into that particular current which comes out of the positive polarity, that is I. So which I can write it as what? I is the resultant current which flows in this direction, and I2 is in alignment with the I, and I1 is opposite. So you can write that as what? You can write that as I2 minus I1. Okay, I has been written as I2 minus I1. Now coming to the power delivered by this current source, power delivered by this current source. So I will write it as PDS, indicative of the power delivered by the dependent source. Now what I will do, I need to know the current source value. Yeah, it is 0.2 VA, it is 0.2 VA, it is 0.2 VA multiplied by the voltage drop across the current source, which has got the positive polarity coinciding with the arrowhead. So this is the voltage drop, so VDS, and it has got what? Positive polarity coinciding with the arrowhead, So 0.2 VA multiplied by VDS is actually PDS. And from the circuit, it is very obvious that you know what is VA? VA is the potential drop across the 5 ohms. And how VA can be found? Whatever the current that enters the positive polarity multiplied by 5. Whatever the current that enters the positive polarity is the resultant of these two. So I1 is in alignment, I3 is in opposite direction. So the current whatever that flows in this direction is I1 minus I3. So what I will now write, VA is equal to resistance value multiplied by the current that enters the positive polarity. The current that enters the positive polarity is the resultant of this, and I1 being in in alignment with the required current, say we will call this as I1. Okay, so 5 into I1. Okay, I1 can be what? I1, my capital I11 I will write, because you should not get confused with this I1. So I11. Okay, yeah, I1 minus I3. So this is what is the current that flows through 5 ohms resistance, which is the resultant current, and which is given as what? I1 minus I3, and why plus I1? Because I1 is in alignment with the required current, and I3 is flowing in the opposite direction. So what you can think is I3, this particular arm, I3 flows in this direction. If you apply KCL here, you will get I11 as I1 minus I3, no doubts in that. Okay, yeah. So now take this and substitute here. So this implies PDS is equal to 0.2 into 5. Okay, into 5 into I1 minus I3, then this VDS. So 0.2 into 5 is 1, so I1 minus I3 into VDS, right. So this is what is the power delivered by the dependent source. Okay. Now if you observe, you require I1, you require I2, you require I3 as well. So how they are to be found? By using the mesh analysis. Okay, by using the mesh analysis. Then one more observation also from the circuit. Whenever there is a current source in the mesh analysis problem, let us all be very careful. Okay, now you find a current source, and what you are observing, this particular arm only belongs to what? This particular arm only belongs to mesh 2, and whatever the current that flows in this direction should be obviously I2. And in this arm or branch, you are observing what? The current source to be present, whose value is also what? Current value is also what? 0.2 VA. So we can dare say that I2 is nothing but what? The current sent by this current source, or the source by this current source, which is equal to what? 0.2 VA. So also from the circuit you can say I2 is 0.2 VA, and VA already we have found it to be as what? 5 times I1 minus I3, 5 times I1 minus I3. So this is now giving you what? I1 minus I3, so I2. Now what we have to remember is, we apply KVL to each of the meshes to get an equation, and now we got an equation, something related to what? The I2, or something related to what? The mesh 2, okay, already. So let me tell you that we need not again specifically apply KVL to this particular mesh. Okay, why? Because already we have an equation associated with that. Okay, even if you apply KVL, it would be redundant. That means without that also we will be able to find the values of the mesh currents. This is what you have to remember. Okay, supposedly if this is 5 ampere, I2 is equal to 5 amperes, then you would have already got one mesh current and one equation less you require. So you need not actually apply KVL to this particular mesh. So this is what we have to remember. So I2 is equal to 0.2 VA means it is as good as knowing the value of the current I2. Okay, so one equation less you require, so you need not apply KVL to the corresponding mesh. This is what you have to remember. So let us all remember that I2 is actually equal to I1 minus I3. Next, apply KVL to mesh 1. Apply KVL to mesh 1. So let us start from here. So plus passive circuit element, I told passive circuit element drop is always what? Plus 5 into, you are applying KVL to mesh 1, right? So I1 minus I3, because 5 ohms is shared by 1 and 3. And now you could have written plus VA also, but again plus VA would be substituted as what? 5 times I1 minus I3. So VA's writing in terms of VA only will increase the unknowns. So let us write the terms only with respect to what? The mesh currents. So plus 5 into I1 minus I3. Next plus 7.5. We have come here plus 7.5, blindly plus 7.5 into this particular element is shared by these two. So I1 minus I2. Then plus 50, so minus 125 is equal to 0, So when you arrange this equation properly, you will get what? 12.5 implies 12.5 I1, okay, 5 I1 plus 7.5 I1. So then minus 7.5 I2, okay, minus 7.5 I2, okay, minus 7.5 I2. Next minus 5 I3, minus 5 I3. Then 125 minus 70, minus 50, which is actually equal to 75. Now I will substitute what? 12.5 I1 minus 7.5 I2 as I1 minus I3, because you know I2 you have found it as I1 minus I3, minus 5 I3 is equal to 75. Now this equation can be rearranged to get what? 5 I1, 12.5 minus 7.5 I1, 5 I1 plus 7.5 minus 5 I3, so which turns out to be what? 2.5 I3, so which is equal to 75. Call this as equation 1. Now we got equation 1. Now next KVL, had this current source been not there, you would have applied KVL here, but already we got an equation related to that, or we got a value related to what? I2, so you need not apply KVL, straight away we will apply KVL to mesh 3. So apply KVL to mesh 3, apply KVL to mesh 3. So we will start from here, plus 17.5, and you know 17.5 is not shared with any of the other meshes, so plus 17.5 I3. So we come here plus 2.5 into I3 minus I2, because this is shared by 3 and 2. Then plus we are going in this direction, plus 5 into I3 minus I1. Since 5 ohms is shared, you are applying KVL to mesh 3, we can blindly write the potential drop across the passive circuit element as plus 5 into I3 minus I1. This is equal to 0. And you know this implies you can write this as ultimately minus 5 I1, minus 5 I1, then minus 2.5 I2, minus 2.5 I2, then you have 25 I3. 25 I3 is equal to 0. Obviously 17.5 I3, 2.5 I3 plus 5 I3, 25 I3 is equal to 0. Next I will substitute I2 as I1 minus I3. So minus 5 I1 implies minus 2.5 I1 minus I3 plus 25 I3 is equal to 0. Next I will have an equation. As rearranged equation as minus 5 I1, then minus 5 I1 minus 2.5 I1. So put together it will be minus 7.5 I1, then minus into minus plus 2.5. So 2.5 plus 25 plus 27.5 I3 is equal to 0. Call this as equation 2. Now solving 1 and 2, we get I1 as 13.2 amperes. I1 as 13.2 amperes, and I3, okay, because when we solve 1 and 2 we get I1 and I3. I3 we will get it as 3.6 amperes. Then I2 is I1 minus I3, already we know this. So we will get it as 13.2 minus 3.6. so which turns out to be 9.6 amperes. So we got all the mesh currents. So we can easily find what? The power delivered by the sources now. Okay. So P 125, so is now equal to 125 I1. This was shown long back. So 125 I1 is 13.2, and when you multiply that, you will get 1650 watts, and you got the power delivered value as positive. So in fact, is the power is actually what? Delivered. Power is delivered. Next, P50 is actually 50 times of I2 minus I1. I2 minus I1 is nothing but I, which is going in this direction, and let us calculate that 50 into I2 minus I1. I2 minus I1, you will turn it to 9.6 minus 13.2 will be minus 3.6. Minus 3.6 means, this I2 minus I1 was I. Okay, I was I2 minus I1. So minus 3.6 means I is not actually in this, is not in this direction, but is flowing in this direction. So this is obviously what? Absorbing the power. So you will get minus 180 watts. So implies what? Power is absorbed. Power is absorbed. Okay. Yes. So if this actually whatever we are calculating is the power delivered value, we got it as negative, which is the indicative of the fact that power is absorbed. Next, power of the dependent source. Power of the dependent source, we know it is equal to what? Okay, we have derived 0.2 VA into VDS, and which was found to be what? I1 minus I3, and then into VDS. Now we don't have any problem in substituting I1 and I3 because we have already calculated, but VDS has to be calculated. VDS can be calculated by applying KVL to this particular mesh, or to this particular loop, or to this particular outer loop. Okay, no problem. But we will always consider that particular closed path wherein there is minimum number of components. Okay, that outer loop will help our cause. This is anyway constant, and this particular resistance is not shared by any other mesh. So the potential drop will across this will have only one term, unlike what? 2.5 into I3 minus I2, you will have two terms eventually leading to. So we will consider what? The outer loop. So apply KVL. The outer loop we will identify in this way. KVL to the loop. So 17.5. It is not a mesh, please remember. Okay, because this can be further divided into some more closed paths. So we are finding the voltage drop by considering the outer loop. 17.5 I3. Okay. Now one thing what you have to remember is, in the case of application of KVL in the loop, whenever you come across the passive circuit element, blindly the potential drop will have what? Plus. Then the resistance value or the impedance value, in this case 17.5, into that particular current which is in alignment with the KVL direction. Okay, of course. Now we are identifying the KVL to the loop. We will identify the loop as what? 17.5 ohms, then what? 0.2 VA, 0.2 VA, then 125 volts, then back to 17.5 ohms. So we are considering the outer loop. First is what? Plus passive circuit element. So potential drop across this blindly plus into resistance value 17.5 into that particular current which is in alignment with the KVL direction. KVL direction is clockwise. So which is that particular current which is in alignment with the KVL direction through this resistance? It is nothing but I3. I3 is considered to flow in this direction, right? So I3 is in alignment with the KVL direction. So I3 I have written. So then minus VDS. So no need of identifying polarities of the potential drop across the passive circuit element. In the case of KVL being applied to any loop, let me reiterate the drop, how to find? Plus 17.5 into that particular current which is in alignment with the KVL direction. Had the KVL been considered in the anti-clockwise direction, what you would have written? Plus 17.5 into that particular current which is in anti-clockwise direction, which in this case would have been minus I3. But we have considered the KVL in the clockwise direction. So that particular current which is in alignment with the KVL direction is I3. So plus 17.5 I3. Next minus VDS. Next minus 125 is equal to 0. So minus VDS minus 125 is equal to 0. When we solve this, this implies VDS is equal to VDS is equal to 17.5 I3 then minus 125. So this turns out to be I3, you know, 17.5 I3 we got it as somewhere around 3.6 minus 125. So which turns out to be minus 62 volts. So you got this VDS as negative. So this is the indicative of the fact that the actual positive polarity is not here but here. So even this is what? Absorbing the power. Okay, because I have told long back that if the current source is delivering the power, always the potential drop across it will have positive polarity coinciding with the arrowhead. But with the value calculated by considering that, you have got it as what? Negative. So what you can say that the actual positive polarity is at the top, negative polarity is at the bottom. Okay, so no problem, we will still calculate the power delivered value only, we will end up with a negative value, that is all. So PDS is now equal to, so 0.2, so here we have PDS is I1 minus I3 VDS. So I1 minus I3 into VDS, and I1 is 13.2 minus I3 is 3.6 and VDS is minus 62. So which is 9.6 into minus 62 turns out to be minus 595.2 watts. So this is power delivered value. This is power delivered value. So what you can say now? What you can say? Okay, this implies power is absorbed. So what I can conclude now? What I can conclude now? This delivers the power of 1650 watts. This absorbs the power of 180 watts. This actually, this current source basically absorbs the power of 595.2 watts. Okay, so that's and our objective was to calculate the power delivered or power absorbed value of all these sources, which we have done effectively and by using what? Mesh analysis. So this actually completes the problem. Now we will go to the next problem. We will go to the next problem. So all those things which I have explained are appearing on the slides here. Okay, now we will take up this particular problem. We will take up this particular problem. Of course, here I will not be doing any board work. Okay, so find the power delivered by the dependent source in the network shown. Okay, that is in the figure 13. Use mesh analysis. Now dependent source is here, and what you can observe here is the dependent source value is 20 IA. That means the voltage value here is actually controlled by the current that flows through 50 ohms, that is IA, that is IA. So you know, this is the current controlled voltage source. Now our objective is to find the power delivered by, this dependent source. Let us see. Now what I have done, the problem is again written but with the meshes and the currents identified. Say this is mesh 1 with the current I1, this is the mesh 2 with the current I2, this is mesh 3 with the current I3. Now from the circuit, IA is I2 minus I3, obviously yes, IA is the current that flows through 50 ohms, which is actually shared by what? The mesh 2 as well as mesh 3. And IA, if you observe, it flows from top to bottom, so I2 is in alignment with that, I3 is opposite to that. So IA can be easily written as I2 minus I3. Okay. Otherwise what you can do, you consider, you know, I2 to flow in this direction because this particular arm only belongs to mesh 2. And you consider what? The I3 to flow in this direction. So IA to flow in this direction. Calculate IA by KCL, you will get the same thing. IA is equal to I2 minus I3. Okay, now let us calculate. Let us see. Power delivered by the dependent source, PDS, which is equal to 20 times IA. I have told you earlier that it is the voltage source value, 20 IA, multiplied by the current that comes out of the positive polarity. Now whatever the current that comes out of the positive polarity is I2 here. I2 here, because this particular arm only belongs to mesh 2 and the current whatever that flows through should only be I2 and it is coming out of the positive polarity. So 20 IA into I2 is actually power delivered value. But IA is already told it is I2 minus I3. So 20 times I2 minus I3 into I2. Okay, so this is so we need to calculate I2 and I3, substitute in this to calculate what? The power delivered by the dependent source. Now apply KVL to mesh 1. So apply KVL to mesh 1. So first we start from here, plus 5 I1 because this is not shared by any other mesh. So plus 5 I1. Next plus 15 into I1 minus I3 because this is shared element by two meshes 1 and 3. and we are applying KVL to mesh 1, so I1 minus I3, then plus 10 into I1 minus I2, then minus 660 is equal to 0, which can be properly arranged to get what? 30 I1 minus 10 I2 minus 15 I3, which is equal to 660. We will call this as equation 1. Next, apply KVL to mesh 2. So, here is the mesh 2, here is the mesh 2. So, plus 10 into I2 minus I1. Now, 10 ohms is actually shared between 1 and 2. We are applying KVL to mesh 2. So, it has to be what? Plus I2 minus I1. Okay. So, plus 10 into I2 minus I1. Next, plus 50 into I2 minus I3. Okay, minus 20 IA. So, minus 20 IA. In the next step, what we are writing? Plus 10 into I2 minus I1 plus 50 into I2 minus I3 minus 20 IA will be substituted by this value I2 minus I3. So, I2 minus I3 has been substituted. When we rearrange this equation, we get it as minus 10 I1 plus 40 I2 minus 30 I3 is equal to 0. So, which will be called as equation 2. Now, apply KVL to mesh 3. So, 25 I3 you can observe. So, 25 I3. Next, what we will write? Plus 50 into I3 minus I2. Next, plus 15 into I3 minus I1. Okay. So, is equal to 0 obviously. So, that is what I have written, 25 I3 plus 15 plus 15 into I3 minus I2 plus 15 into I3 minus I1, which is equal to 0. When we arrange this, minus 15 I1, then plus minus 50 I2, then 25 plus 50 75 plus 15 90 I3 is equal to 0. After solving this, we get what? Equation 1, 2 and 3 can be solved, and we get I2 as 27 amperes and I3 as 22 amperes. I1 not required actually, even in the calculators you will get in one shot I1, I2, I3, but I have not indicated here because that is not required as far as the power delivered by the dependent source is concerned. So, I2 is 27 amperes, I3 is 22 amperes. So, when I substitute these two in the power delivered equation, so 20 into I2 minus I3 into I2, 20 into, okay, I2 minus I3 is 5, I2 minus I3 is 5, then I2 is 27, we get 2700 watts and power is delivered, in fact, because you got it as positive value, and in fact whatever we have assumed, it is correct, that is power is actually delivered. So, today we have seen the illustration of the mesh analysis and the problems related to the mesh analysis. Tomorrow we will start off with the AC analysis. Thank you.